Thank you for joining me, and thank you to LabRoots for facilitating this webinar. Today we're going to go over terpene trends and an exploration of nationwide cannabis testing data. My name is Yasha Kahn. I've been in cannabis testing for over a decade at MCR Labs across 4 states. And since this conversation is about terpenes, first, we should go over what are terpenes. You go outside and you see trees, some marijuana is growing, cannabis, tomatoes in the garden, mushrooms, soil, maybe some mold is growing somewhere. And all of those things are made up of molecules, and some of those molecules evaporate at room temperature. When they evaporate, they enter the environment, and when we inhale, those molecules go into our noses. Those molecules are volatile organic compounds, most of them. Volatile meaning evaporate at room temperature. Organic means that they're carbon-based molecules. There are a lot of sources for volatile organic compounds. Everything that produces a smell likely has multiple compounds that represent what the smell is. And the bouquet of smells come from the bouquet of molecules, or the smell comes from the bouquet of molecules that it produces. And there's multiple different kinds of volatile compounds that are responsible for this smell. And we, as humans, are able to smell these compounds at very small amounts. So, for example, we can smell soil or bacteria at 5 parts per billion, terpenes at maybe 10 parts per billion. And all these compounds are throughout in the air. But we're talking just about terpenes. And if you were to walk into almost any dispensary across the country or wherever you are, you're going to see a chart that looks like this, one that says that a terpene may help with a specific medical condition or an ailment, or may be more energizing or sedative. I'm not going to comment on what's true, what's not, how much evidence we have on anything, but terpenes have become a big part of the cannabis conversation. And terpenes are only a part of cannabis. First and foremost, cannabis is a plant, and it has plant matter that make up the majority of the flower that we consume. It has lipids and waxes, water, cannabinoids, terpenes that make up 1 to 5%, and then other compounds like flavonoids, esters, sulfur compounds. Terpenes are also not the only compounds on cannabis that contribute to smell. There are also esters, sulfur compounds, possibly mold, and like any plant material, when you break it apart, you're likely going to smell chlorophyll also. There's some questions that can only be answered with enough data. Having a single product or 10 or 100 product results wouldn't be sufficient to really understand, but across the entirety of all cannabis, what are terpenes? What role do they play? And here's some of those questions that I want to explore today. Which terpenes are most abundant in cannabis? What's the average total terpene percentage in flower? Why do some labs report higher terpenes than others? Are cultivators boosting THC at the cost of terpenes? And how can terpene data help identify cultivars? Since we're not going to be talking about terpenes, but about terpene data and terpenes from the perspective of data, we should take a quick look at what data sources we have. There are 2. Leafly, the company, worked with labs across the United States, a lab in each of Washington, Oregon, California, Alaska, Michigan, and Florida, and got terpene testing data and made all of that data public. And I sent Freedom of Information Act requests to every state in the country for their cannabis testing data, Nevada, Missouri, New Jersey, and Maryland made their terpene data available. Together, this forms a rather large data set covering 10 states, data from 35 laboratories, and 250,000 flower samples, nearly 250,000, on which we have some form of terpene data. The term total terpenes, when we say that, we're talking about the sum of all terpenes that are detected in flower. But there's a limitation there. There are 300 to 400, if not more, terpenes that are in cannabis. There are no labs that test for all of these terpenes. When surveying labs, I found that the average number of terpenes that are tested for in cannabis testing labs is 34. And the 3 labs with the highest number of terpenes tested are Pure Vita Labs in Rhode Island, Spectral Fingerprints out of Slovenia, and Laboratory Phytochemia out of Quebec that tests for 83 terpenes typically and up to 170. I'm going to refer to Laboratory Phytochemia a couple times throughout the presentation, as they do have the biggest list of terpenes that they test for. Some terpenes are more abundant in cannabis or are found in higher quantities than others. The top 3 terpenes are limonene, myrcene, and caryophyllene by amount of each of those compounds found. On the left, we can see each terpene and how much of it is detected on average across all samples tested in a laboratory that tests 40 terpenes. And the 3 terpenes that I said, limonene, myrcene, and caryophyllene, make up 44% of total terpenes. Some terpenes appear and are detected in every single cannabis flower that's tested, and some terpenes are rarely found. The central graph shows this. Again, limonene, caryophyllene, and myrcene are found in every or almost every single flower that's tested. Camphor, on the other hand, is rarely detected. That's the one at the very bottom. And menthol also, rarely detected. Then the question that we can ask and then answer is, when a terpene is detected, how much is detected? So we now remove all times when a terpene is not detected, but if it makes an appearance at all, how much is there on average? And again, we see that myrcene, caryophyllene, and limonene are at the highest amounts, but camphor and menthol, those that rarely appear, when they do appear, they're in a relatively significant amount. And that was strange because they seem like interesting outliers. And when discussing this with multiple labs, it seems that likely these 2 compounds are found in cannabis flowers because these flowers have been infused with terpenes that were derived not from cannabis but from other plants. And so although rarely found, when found, it's an indicator that they are not naturally occurring in cannabis. Here's the same graph as we saw earlier, showing the average amount of each terpene detected by Laboratory Phytochemia. That's the lab that is in Quebec and has the biggest list of terpenes that is tested, 83 terpenes. Myrcene, caryophyllene, and limonene are, again, the ones responsible for the biggest amount of total terpenes. And they make up 37% of total terpenes. There are 2 terpene families, celanine and eudismane, that are not tested for by almost any other lab. And they are families of terpenes that make up a significant portion of total terpenes at Laboratory Phytochemia. Terpene concentration range in flower. I was curious, what is total terpenes? How much is the average? What do we see on average in terms of total terpenes as part of the plants? I thought that maybe around 2% of the average cannabis flower is terpenes. Others who I asked said that they believe it's somewhere over 3%, possibly 4%. And with this data, we can answer this question. So looking at all the data that we have from 2018 through 2024, these 7 years, the average total terpenes is 1.66, so under 2%. But that doesn't answer the question of what is the average amount of total terpenes, because as we can see, total terpenes is increasing over time. In 2018, it was around 1.5%. In 2023, it seems to be higher. And since 2023 is the year where we have the biggest amount of data through the Freedom of Information Act requests, we can take a look at just 2023 total terpenes, and we see that the average is right around 2%, maybe slightly under. And rarely are products found, or only 1% of flowers has more than 4.11, 4.11% total terpenes. This is based off of data acquired through the Freedom of Information Act, and doesn't represent the labs with the highest number of terpenes that are tested. So we can take a look at laboratory phytochemia, the laboratory that tests more terpenes than any other, and their total terpene average is 3.4, which is significantly higher than what we see in most labs, and that is because they test for more terpenes. So the conclusion of this section, kind of obvious, is that more terpenes tested means higher average total terpenes. Next, the relationship between THCA, and terpenes. This pie chart represents the average cannabis flower. It has some plant matter, lipids and waxes, water, terpenes, cannabinoids, flavonoids, esters, sulfur compounds, etc., and some wiggle room, because sometimes there's a little bit more moisture or water. Cannabinoids maybe more than the 22%, maybe less. So there's some wiggle room because it's a plant, and they're not all exactly identical. And the question is, what happens when we breed for higher cannabinoids? What happens if the flower is not at 22% total cannabinoids, but at 35% total cannabinoids? Something has to decrease, because we can't have more than 100% when you add up all of the compounds. And so we do away with the wiggle room, but it's still significantly over 100%. That means that something has to give. There needs to be less of something for there to be more of cannabinoids. And the question that we can answer with this big data is, does breeding for high THC leave less room for terpenes? When I started to examine this, my assumption was pretty clearly yes. More cannabinoids or more THC is going to mean a decrease in terpenes. When we look at all the data across the US, we see that there is a correlation between THCA and terpenes. As THCA increases, total terpenes also increase. When we zoom in on a single state, this is just Nevada, we see that the correlation is tighter, as in it's more clear that as we increase in THCA, total terpenes also increases. And when we zoom in further and look at one single lab, the correlation is even stronger. THCA increases, so does total terpenes. Now, we have gone through the general statistics about terpenes, their relationship to THCA, what are the dominant terpenes, and that total terpenes, we know what the average is, and that it's growing over time. Now let's dive a little bit deeper and take a look at the relationships between terpenes. Here's a scatter plot, and this shows the relationship between humulene and caryophyllene. These are two terpenes. And we can see that there's a pretty solid line that's formed in blue by all of the dots. Each dot represents an individual sample that was tested. The position of each dot represents the ratio of humulene to caryophyllene. And it seems that most of them line up right in a pretty firm line. And I added a line of best fit to a line in yellow to show that most results for humulene and caryophyllene align on this line. The slope is pretty set. It has a linear relationship. As caryophyllene increases, humulene also increases. When we look at humulene versus caryophyllene in all original glue samples, we see the same thing, that they all align. Same thing with Blue Dream. They align on that same slope. And we can't tell the difference between original glue and Blue Dream if all we see is the ratio between caryophyllene and humulene. But we see something different when we look at alpha pinene versus beta pinene. These are two other terpenes. We see that there are multiple trends, three different directions that seem to that are seen in the data. And this suggests that there are multiple subgroups in the data. On the left, we see all alpha pinene versus beta pinene results for original glue, a cultivar, a cannabis cultivar. On the right, we see the relationship between alpha pinene and beta pinene for Blue Dream. The yellow lines represent lines of best fit, and we see that the slopes differ for these lines. And most of the samples align very neatly for Blue Dream, and most of them align very neatly for original glue. But right away, I want to ask the question, what are these? Why is it that most samples align and have the same ratio for original glue, but there are some that are outliers that don't conform to what the majority of samples show? And so we're going to zoom in on this graph right here, the one on the left, and it's the one on top, graph A. Again, it shows alpha pinene versus beta pinene for original glue. The bottom graph shows, graph B shows limonene versus beta pinene, also for original glue. And every dot in graph A is also represented somewhere in graph B. And we have the trend lines that show the majority of samples have this relationship, this slope, this relationship between alpha pinene and beta pinene, or limonene and beta pinene. We drew a confidence interval, or a rectangle, around the majority of samples for alpha pinene and beta pinene. Most samples, or nearly 90% of samples, fall in line and have the same ratio. And everything that's outside of that rectangle, I marked in red. All of those darts are red. And the question that I had was, are the outlier samples, the ones marked in red in graph A, also the outlier samples in the bottom chart in graph B? Are outliers universal outliers, those samples, or are they only going to be outliers for a specific compound, a single compound? What we found was that yes, 11% of the original glue samples were consistent terpene pair outliers. They don't conform across these pairs of terpenes. I have no idea why. It could be that it's because they're different phenos. It could be that it's samples that are misnamed. They're not actually original glue. But we do have this data, and we see that there are some ways in which we can identify outliers. To summarize this section before applying it, some terpene pairs are not useful in identifying cultivars. For example, caryophyllene versus humulene, the ratio is pretty much always the same. Some terpene pairs are useful for identifying cultivars. Alpha pinene versus beta pinene, for example, is seems to have a specific ratio, those two terpenes, per cultivar. And we've identified a way to systematically identify outliers. Now let's apply this. This graph shows all of the original glue samples in the Leafly dataset. The x-axis shows the terpenes, the y-axis shows the amount of each terpene detected, and each line is a unique sample in that dataset. We removed all samples by cleaning the dataset, and what we found was a very set ratio, the same ratios we found earlier, where there is a known ratio of alpha pinene to beta pinene and beta pinene to limonene. And we also see that there is, once outliers are removed, we can see that humulene versus caryophyllene, the ratio is, as we saw in earlier slides, around 1 to 3. We did the same thing with blue-green, where we can see once outliers are removed, the ratio is pretty set for alpha pinene versus beta pinene and beta pinene versus limonene. A lot of samples, most samples, have a ratio that is, as we saw earlier in the scatter plots. And humulene versus caryophyllene, again, is relatively static across all samples. And this is an approach that may be useful in identifying cultivars or cultivar families. To summarize, total terpenes reported is increasing over time. As THC increases, total terpenes also increase. The most abundant terpenes are myrcene, caryophyllene, and limonene, and unique terpene ratios can be used to define or describe cultivars. This work was influenced by a lot of people, and a lot of people helped to contribute to this work. Many of them are listed here, and a big thank you to everyone that contributed. Almost all of the data used in this presentation is available through the QR code on the right. I am available for any questions on terpenes, this presentation, or any other cannabis testing questions that you may have. My email can be found on this page, yasha@mcrlabs.com, and this platform has a field for asking questions that will also come to me, so please send questions. If you find any interesting analysis in the data, if you find any fault in my analysis, please let me know. I would love to discuss, and I would love to learn more and be a part of these kinds of conversations. Thank you for joining me, and thank you to LabRoots for facilitating this conversation.